the requirement specification. Here you can see the learning objectives of this presentation, of this lesson. At the end of the lesson, then you should be able to understand the properties of an engineering requirement and know how to develop requirements that meet the properties of the system or design. You should be familiar with engineering requirements commonly used in electrical, electronics, and computer engineering. Be able to understand the properties of the complete requirement specification and learn steps to develop a requirement, and be able to conduct advanced requirement analysis techniques to identify design trade-off. When we look at the dictionary, American Heritage Dictionary, specification is defined as a statement fully describing something to be built. We simply in design projects try to identify or develop a collection of engineering and marketing requirements that your design must satisfy in order for it to meet the needs of the customer or end user. So starting point, as you can see here, is the need, customer need, and we have already discussed the customer needs identification, as well as problem statement in previous presentation. In this presentation, I will be frequently mention a standard, IEEE standard number 1233, 1998. It's an important standard to mention for developing requirements. There are three stakeholders according to IEEE standard: customer, which will be important for marketing requirements; environment, from which there may be some constraints or standards that may limit the design or impact on the design; and technical committee, where we are engineers who design, implement, test, or manufacture the system. So the IEEE guide for developing system requirement specification. So the standard number given in previous slide. When we are developing a system requirement, there are three stakeholders, as we have listed in previous slide: customer here, and environment, and technical committee. Technical committee provide technical feedbacks to develop system requirements, and there are somehow representatives in this team, system requirement team, and there may be a feedback coming from here, and then will be discussed by the technical committee engineers, and then technical feedbacks will be provided to develop the system requirements. In customers, we have product or marketing requirements, which is very much related to the need. And these requirements are simply customer feedback to be used in developing system requirements. There may also be a representative. There may be somehow flow from the system requirement stage or process to customers. So there is a closed loop here and here. On the other end, for environment, there are constraints and standards imposed by the environment, and these are directly they have impact on the system requirements, and there is usually nothing we can do to change these constraints or standards. So there is no feedback from the system requirements to the environment. Okay, let's see then marketing and engineering requirements. Marketing requirements are the inputs from the customer directly, customer need, and they are usually simple, easy to understand, and very much related to the systems or products available in the market. A simple and very common marketing requirement will be the system should be easy to use, for example. That's quite important for many products. On the other hand, for engineering requirements, we have some short statements that address a technical need of the design. Technical need of the design. An example is given here, as you can see. The system should be able to supply 50 watts of power. It's fully technical, and it somehow refers to the design details. It's concepts that you will be developing. Requirement specification, then, which is the subject of this lesson, complete set of all requirements, including marketing and engineering requirements. Let's see the properties of engineering requirements. An engineering requirement should be abstract, somehow verifiable, unambiguous, and traceable. These three properties are quite important, and we have to somehow inspect when we write an engineering requirement whether it meets this or it satisfies these properties, or it has these properties or not. Abstract means we do not mention about the solution in engineering requirement. We should simply specify what the system, what the design will do, not how it will be implemented or which design concept will be used. No technical implementation or design activities should be mentioned in engineering requirement. Verifiable, there should be a way to measure or demonstrate that the requirement is met in the final system realization. So at the end of the design, we should be able to measure or demonstrate that the requirements is met. Unambiguous, there should be clear meaning in engineering requirement. There should be short, complete sentences, no ambiguity in the engineering requirements. Traceable, every engineering requirement somehow is targeting marketing requirement, so should be traceable marketing requirements. At the end, engineering requirement must serve to the customer's need. There is one more property for engineering requirement, which is realism. Every engineering requirement should be or must be realistic. if we give some figures, as we have shown in previous slides, 50 watt of output power, for example, we have to make sure that this number, this figure is realizable. In the next slide, we'll be showing that there are some methods to do this. Anyway, the engineering requirements that we are going to develop should be technically feasible. And usually we use benchmarking techniques to identify similar systems or designs in the market or in open literature. And then we take the performance parameters there and try to compare our requirement, engineering requirement, with those given in the products. Constraints, as we have shown in IEEE standard from the environment, there are two parameters or constraints and standards are used in developing in developing engineering requirements. A constraint is usually from the users or stakeholders, and there may also be some environmental constraints, and we have to somehow we have to satisfy the constraints when we are developing engineering requirements. An example is shown here. The system must use an ARM Cortex-M series processor to implement processing functions. This could be a constraint coming from either the operational conditions, the environment, or a stakeholder from the user or customer. Standards, as a definition, it's established way of doing things that ensure interoperability, and with the standards, we are able to have products working together. There are three levels of use of standards. As you can see here, there are two course codes in which we'll be using standards. At user level, that is the design phase, and we do not need to know the technical details of standards. In this course, EEE 392, we'll be designing a system, and we do not need to know the technical details of standards, but we have to somehow identify which standards are applicable to our design. In the next stage, where we have implementation, and this is usually applicable to the course, senior level courses, EEE 492, for example, where you have to know the details of the standards, and you have to understand how you implement, how you satisfy those standards. So that is the implementation level, which is not applicable to this course. And there is also a development level where there may be new standards developed by engineers from different organizations. That is the level where some big companies and some regulatory organizations come together and try to develop new standards. Here you can see some types of standards: safety, testing, reliability, communications, data formats. documentation, design methods, programming language, connector standards, and meta standards. You can go through those types of standards from the textbook or from any reference book. Safety, as we can understand, the design should be safe enough, and there may be some standards related to safety, and we have to identify those safety standards, and then we have to satisfy while we are designing our system to those safety standards. Testing is somehow extended or broader version of safety plus performance. So in testing, there should be some performance parameters as well as safety. Reliability is how our design is reliable. Later, at the end of the semester, we'll be discussing reliability. It's quite popular in military projects. Communication is about how your design communicates with others, with the environment. Data formats is about sharing information, how you code the data, how you transfer the information from your design to others, for example. So somehow it's very much related to communication type. Documentation, there may be some standards regarding with documentation, especially technical reporting. As far as I know, ISO, for example, has some documentation standards. Design methods, these are quite applicable in our projects. UML for software development, Unified Modeling Language, or HDL, Hardware Description Language, which is quite applicable and quite common in electrical engineering. Programming language have also standards. Syntax should be standardized so that if you use several different compilers, then the code should be portable. And when we go to the hardware, circuits, and systems, there should be connector standards so that any equipment or model or component should be connected to others easily. So there should be cable interfacing, connector standards. Meta standards is a combination of multiple standards. RS 423, for example, could have a meta standards because it has both physical, electrical, and some functional standards. It satisfies. So this could be an example of meta standards. So let's see some categories of requirements in electrical engineering. There are many. I have just here listed a few in this slide and the next slide. These are quite practical and applicable to your project. Performance is one category. There should be an engineering requirement regarding with the performance of your design. Here you can see an example. The system should detect 90% of all human faces in an image. Could be a performance requirement. Reliability and availability. The system will have a reliability of 95% in 5 years. Energy, environmental, health and safety, legal, maintainability, manufacturability, operation and usability. For example, for usability, users of the system should be able to learn 80% of its functionality within 2 hours. So that's quite, as you can see, clear, verifiable, and traceable. It's very much related to marketing environment usually. Properties of the requirement specification from the IEEE standard again. Normalized set. There should be no overlapping or redundancy between the engineering requirements. Complete set. All the needs of the end user as well as the needs required for the system implementation should be addressed in requirement specification, so engineering requirements. There should be no contradiction between the engineering requirements. So consistent, they should be consistent. Bounded, there should be some bounds for the target values. It should be minimum acceptable bounds. We usually refer to the minimum values. We try to be at minimum level so that we can easily verify it. Modifiable, usually at the beginning of the projects, we do not have a clear picture about the concept that we are going to implement. So the target will be somehow unclear. So we have to be careful when we are developing engineering requirements. Then initially we usually develop some baseline requirements, and then later with the experience with some concepts that we'll be developing, we can modify those engineering requirements. Of course, we have to agree with the user and the technical team we are working with. Okay, here we can see a case study. That's iPod hands-free device for drivers. And here you can see some marketing requirements. There are 7 marketing requirements you can see there. It should be portable, easy to use, be able to fit and operate in an automobile. So these are quite common marketing requirements for a hands-free device for automobile drivers. In the table, you can see the list of the engineering requirements, and each is somehow targeting marketing requirement. So, for example, this engineering requirements is a traceable marketing requirements, and it targets market requirements 4 and 6. And there's a justification here why we develop this or why we define this engineering requirement. For the second engineering requirement, there are 4 marketing requirements that we are targeting. And here you can see the justification of this requirement. We are continuing on this case study. Here you can see again an engineering requirement, accuracy, you see with some figures here. And here it seems that there is a research on which this requirement based. And this again targets market requirements 4 and 6. So as you can see, they are very clear, short and complete sentences. And they should be traceable, they should be feasible, and they should not be about the solution. They should be about what the system will do. So there are some advanced requirement analysis methods. Here we have one shown in this slide. That's a trade-off matrix among engineering and marketing requirements. And here we consider our audio amplifier, which is well known and popular in the market. Here you can see marketing requirements on the left, and here you can see engineering requirements. And we simply give some correlation symbols. Here, if there is a positive correlation, we use an upward arrow. And if there's a negative correlation, we use a downward arrow. If these correlations are strong, then we use double arrow, upward or double arrow. downward. Engineering requirements might not be easy to understand sometimes. For example, here, total harmonic distortion. This could be a very technical concept for you, but this is an important requirement for an audio amplifier. And here you can see symbols, minus or plus. Minus means that increasing that requirement is not desired. If it is positive, then increasing that requirement is desired. So simply, we would like to have better sound quality, so we use plus. We'd like to minimize the cost, so we use minus. Similarly, we'd like to minimize total harmonic distortion, so that's minus. We'd like to maximize the output power, so we use plus. So here you can see the correlation. Simply, that's a correlation matrix. We see here we have a strong positive correlation between sound quality and total harmonic distortion, while we have a strong negative correlation between sound quality and cost. On the other hand, for the dimension and installation or easy installation and dimension has a positive correlation. So by simply constructing such a matrix, we can focus on which requirements are more important or to be used in the design. We can also make a matrix for engineering requirements, among the engineering requirements. Here again, you can see total harmonic distortion right here. So that's going to be a diagonal matrix because each engineering requirement is related to other requirements here. And we can see the correlations. Total harmonic distortion and output power has negative correlation, while output power has positive correlation with the efficiency. Sorry. Finally, while we are targeting some figures in developing engineering requirements, we have to use benchmarking, usually, what we call competitive benchmarking. We look into the similar products in the market and then study the performance or data sheet, all whatever available in the market. We study them carefully and then identify the engineering requirements and then compare our targeted requirements, or we determine the targeted values based on the figures of those products. For example, here, for car audio amplifier, it seems that there are two audio amplifiers in the market, Apex and Monster. I'm not sure these are valid trademarks, but let's suppose that these are two products in the market, and we'd like to determine the engineering requirements here, the values, the figures here. For Apex Audio, that's 0.05%. For Monster, it's 0.15%, and we somehow determine in between these two, so 0.1%. This could be feasible in the sense that if you'd like to commercialize our design, then we have to target a total harmonic distortion somehow comparable with those in the market. So we can choose something like this. For power, it's 30 watt here and 50 watt here. So we simply try to be more conservative and close to this 30 watt. For efficiency, that's 70% and 30%. So we, again, seems to be conservative and choose 40% close to this monstrous amplifier. For the cost, here we are quite competitive in the cost, as you can see. It's $100, while for Apex and Monster, it's more than our targeted cost.